welcome back to another episode of Introduction to Computer Networks at NTU. Well, good morning to Josephine and Kenny. And just like the regular Wednesday sessions, we have nothing really new to announce, so we'll go ahead and start with the topics today. So we just finished talking about RDT, the general design principle, okay, from version 1, 2, all the way to 3. We know that RDT3 will work generally for bit errors and packet losses. But the thing is this, RDT 3.0 does not work all that well. So in this video talking about the issue with RDT, you will see Polly introducing a new term, a metric called utilization. And you will see how RDT 3.0, being a stop and wait type of RDT, underutilized the capacity between the sender and receiver.
RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay, let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them, there is this link, 1 gigabits per second. And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connections packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, sender is actively sending all the time. So usually the throughput is going to be better. Okay. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again stop and wait until data travel to the network, ACK travel to the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits, and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part, sending the packet and then wait, one wait and another wait. And here I'm ignoring the ACK packet transmission time because ACK packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. So overall utilization on this link is very, very low, 0.00027, too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline. Okay, at time 0, first packet bit is transmitted. So right here, first bit goes onto the link, and it takes this amount of time. That is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time. Okay, that is the packet transmission time, L divided by R. And these bits, it's going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is one cycle. Within a cycle, only this amount of time sender is being active. Okay, only this amount of data is being transmitted. While the entire duration, right, the sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. This is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending one packet and then stop and wait until we can send another one. Now that I show this plot, then you know, yeah, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario.
All right, so that's why we need another generation of RDT called pipelined RDT. So now let's introduce pipelined RDT more formally. You will see illustration that probably contrasts the stop and wait RDT versus the pipelined RDT. And in the second half of this video, you will see there are 2 kinds of pipeline RDT we'll talk about in this course. One is called go back N, the other is called selective repeat. You will see that the 2 of them are the same because they will all track a certain number of packets in flight. And that number of packets they will track is a window of packets. Okay, so that's another new term, a window of packets. And the size of the window, usually we use this term, big N, to represent it. But the 2 kinds of pipeline RDT differ in what ACK means. Okay, in one flavor, the ACK means acknowledging just one packet, but the other flavor says I ACK multiple packets. Okay, and the timer. RDT 3.0 has also timers, that is to track lost packets. In one flavor, the timer meant that I'm gonna keep a timer for the whole flight, whole window of packets. But the other flavor says that let me keep one timer per packet. So these 2 different flavors, they behave differently. They are the same in terms of there's a window of packets they track. They also send ACKs. Okay, that's very basic element in RDT, but the ACK means differently in 2 different mechanisms. And there's timer, that is to make sure that we can track lost packets, but the timer also, in terms of numbers of these timers we keep, differ. All right, so this video is a little bit long, about 6 minutes.
And this takes us to this new class of RDTs called the pipelined protocols. Okay. What it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in flight, I mean that these are just data packets going out, they are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipelined RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence. okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just one bit, right, 0 and 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. Well, the sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because hey, when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay, so there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay, now in the next few slides, what we're going to introduce are just two different flavors of these pipeline protocols. So they are the big categories. First is the go back N. The second is selective repeat. Now one can of course further tune the go back N so that it works slightly differently. Hopefully the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts the two big categories of pipeline protocols. On the left, the go back N. On the right, selective repeat. Right? They are the same this way. Okay. Both of them allow having multiple packets in flight in a round. Okay. Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means, very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back N, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that. But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back N here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. Okay. So the next one is, yeah, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, yeah, we need a timer in order to tell whether a packet is dropped or not. Yes, go back N and selective repeat, both of them implements timer. Okay, but in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back N, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay, and if the first one is acknowledged, there'll be a timer for the second packet that is now the new oldest packet that's not yet active. Okay, so yeah, one timer for a flight of packet in go back N. And the last difference is this. Okay. For selective repeat, when timer expires, the sender only retransmit the unacked packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back N, when the timer expires, it's going to retransmit from, yeah, that oldest unact packet. So all the unact packets from the oldest one to the newest one. All right, so each timer is going to trigger retransmission of the rest of the flight of the packets.
All right, so between selective repeat and go back in, selective repeat, the ACK and the timer, each is for an individual packet. But you see in go back in, they like to take a group of packets as a unit, right? So an ACK is a cumulative. It can acknowledge all the packets before it, before the sequence number in the ACK. And the timer is for a whole flight of packet. And if the timer expires, you retransmit the whole flight of packet. Okay, so selective repeat, individual. Go back in, group. Okay, so keep this in mind. Now, let's go on and talk about go back in more. Okay, the first video is going to explain. Now we keep a window of n packets. We definitely need to distinguish these n packets apart. So in RDT 3.0, we use just 1 bit, right, to tell duplicate packets. But for n packets, to tell n packets apart, yeah, 1 bit is definitely not enough. The sequence number is definitely going to be higher than 1. Okay, so let me explain the sequence number and what the sequence number requirement is. Second is now, we have a window of n. So in the sender side, you will see that the sender reserves some memory space. First, to buffer the packets that are already sent but not yet acknowledged, because these packets might need to be retransmitted. So after sending the packets, you cannot just throw them away. You cannot free the memory space yet, so you keep them around. And then there's also some space that's within the window size n, but the application layer doesn't have more data to send. So those are like available memory slots that allows sender to send more packets. Okay, so that window of n, you will see some packets being sent, but keeping the memory space, and some memory space reserved and ready to send more packet, but not used. Okay.
Now let's look closer into the first categories of the pipeline RDT, the go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number in go back in. If you recall in RDT 3.0, we only allow 1 data packet goes in out without being acknowledged, isn't it? And in that case, we just need 1 bit sequence number to tell the old packet and the new packets apart. But now go back in being a pipeline RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k, subtracting 1. And next, in go back in, or generally the pipeline RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unact packets allowed. Right? In go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is n. Right? So at any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. Okay. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Okay. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. Right? Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. Right? And the last one, so these blank ones are simply outside of the window limit, so not usable. Right?
All right, now you see a bunch of packets sent. The green ones are the ones act. The yellow ones are the one not yet acts. They are still in flight. And then a bunch of memory slots. Some are okay to send more, but some are no, this is beyond n. So yeah, there are memory space in the sender computer, but that's not used up. Okay. Now, next video talks about this. At this point in time, if you receive an acknowledgement from the receiver, right, then some of these yellow packets will need to turn green because they are act. Okay, and you will see that the yellow packets turn into green, and therefore the window, right, the send base needs to change to the first yellow. So you see the window slides over. And one more memory slot used to be blank or gray can now turn blue.
And here, let's assume, okay, send base here finally receive an acknowledgement, and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first unact packet, so we actually need to what? Change it to this packet sequence number. Right? As a result, we shift the window, and it's beginning from here, and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called a sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go back and sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by 1. The next seek num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seek num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed, and the n here is a constant. But be careful though. There'll be scenarios where, hey, all these blue ones are actually yellow, meaning, yeah, the sender does have large message to send, and we are actually exhausting the entire window size to send the message already. In that case, the next seek num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, yeah, there's no blue packet at all. All right, so next seek num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet.
Yeah, so you see the sender side there, keep track of a few important variables, sendBase and next seek num. Okay, sendBase is there to track the sliding of the windows, isn't it? The next seek num is to track the next available open slot for the applications to send more. Now the first blank or the first gray slot is always sendBase plus n. All right. Now next video is trivial. You will hear Polly repeating herself because in go back n, the ACK is cumulative. The timer is for a whole flight. When timer times out, we retransmit the whole flight. So this video is trivial, but right after this video, quiz 21 is coming up.
The rest of the go back n you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right. Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment, another ACK n is received. What does that say? If you recall earlier, yeah, that usually meant, oh, packet n plus 1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at the sender side indicates, yeah, whatever n is plus 1 is a packet that's missing. Timer. Yeah, there is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base, okay, of the in-flight ACK packet train. Okay, so that is essentially this. Yeah, the oldest in-flight ACK packet is always indicated by the sendBase. In a way, yeah, there's a timer associated with the sendBase, essentially. Whenever the sendBase is changed or whenever the sendBase is refreshed, we refresh the timer or restart the timer. If it's a bit unfortunate that we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet, starting from n all the way to the highest number that's not yet ACK. So that means starting from the sendBase all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
All right, that takes us to quiz 21. And let me go to the whiteboard mode, and this is quiz 21. All right, so we have now a go back n sender, and here's the window size n. And you know what? The sendBase is currently 23. Next seek num is 33. And the first gray packet is number 39. Then what is n? Hey, you can calculate it, right? But that's not what I am asking. I'm asking this, Q1. After sending 3 more packets, what are the values of these 3 variables? All right, Q2. After sending 3 more packets, receiving ACK for 27. So Q1, Q2, Q3 are cumulative. So Q2 continue from Q1, Q3 continue from Q2. So Q2 says, after 3 more packets, then something changed, these variables changed. But after that, if we receive ACK for 27, hey, the 3 variables might also change. Okay, and what will be the values of these 3 variables? Q3 continue from Q2. If we receive an ACK for yet another sequence number 32, what will be the values of these 3 variables? Okay, good. Let's go to the score space. All right, so I double checked the slides I used this semester, and this is now correct. Okay, guys, this might require some thinking, so take your time. 4 minutes. Okay, and the bonus goes to the first correct answer. All right, very good. We have a winner. That is Team 9, Anthony. Yeah. Devon, Team 10 was very, very close. Yeah, because when you receive an act for 27, yeah, that is the last packet act. That is the last green packet, right? Therefore, the first yellow, which is what send base is pointing to, will be 28. Yeah, you were very, very close. Okay, so consolation prize. And Ricky, yeah, you want to be the first, I know. Yeah. But you're right for Q3. right? If you receive ACK for 32, yeah, you turn all the yellow packets all the way to 32 green. Next seek num is only changed when there are more data coming from the application layer, when there are more packets sent. And you know what? The gray packet, the blank packet, sequence number, the first gray packet is always changing with the same base. All right? Yeah, I guess after this quiz, you guys now all have a better sense of how the window slides and how these variables gets updated. Receiving X update the first yellow packet sequence number, which is send base. And of course, then you change also the first gray packet sequence number. And when there are more data coming from the applications to send, yeah, you add more yellow packets. You turn some of the blue packets yellow, and therefore the next seek num, the first blue, is changed, is updated. So in a way, you are learning how to implement a TCP sender or a go back N sender. You see? How you track a window of packets in flight. All right, very good. So you see that quiz 21 is very important because then you finally pick up the theory and you can exercise it, and so that you can program it. Good. I'll come back to grade the rest of the teams, okay? And I think that it's now clear. You guys should have no problem tracking these three variables. Now, how about let's talk about the finite state machine of go back N so that it's really, really concrete and you can follow the instructions and implement go back N. Now, the first video is review RDT 3.0. So 3.0 is much simpler. Let's check out the finite state machines again of RDT 3.0. And you will see that essentially at the sender side, there are 4 important transitions. And the sender side of go back N also have those 4 transitions. Okay.
Go back N sender's finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay. So we're starting here. Okay. And there are 4 typical transitions, 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the ACK we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an ACK all right, but this is what, carrying 1, which indicates this is a negative acknowledgement. Right? So in these 2 cases, instead of quickly retransmit, we just ignore. Right? So this is a quick refresh of RDT 3.0.
All right, now go back N sender's finite state machine. Okay, in this video, I talk about 2 important transitions in go back N sender finite state machine.
In go back N sender finite state machine, we also have these 4 transitions: getting a call from above, receiving feedback from the receiver, and it's not corrupted, having the timeout event, as well as getting feedback from the receiver, but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because Go Backend is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packets will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in Go Backend, we have one timer for the entire flight of ACK packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in Go Backend is associated with the first yellow packet, so associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of ACK packets. And the last is straightforward, just increment the sequence number by 1. So this is if the next seek num is within the window. Otherwise, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement. And it's a new one, therefore we could move on. All right, so let's take a closer look at how the move on is like in Go Backend sender. First of all, the checking condition. Get the feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those cumulative ACKs. So inside the ACK, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get ACK num. Okay, so this is a new function call introduced into Go Backend's finite state machine. So that is just a bit abstract, but what it does is to get the sequence number in the cumulative ACK packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is unacked. Hey, makes sense, right? Receiver sends a cumulative ACK. So that ACK carries the sequence number n, which indicates all the sequence number before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that ACK cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet ACKed at this point in time are already ACKed. Okay, so stop timer because there's no pending packet waiting for acknowledgement. Otherwise, restart timer. So we receive a cumulative ACK. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. All right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones certainly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer for the refreshed first yellow packet.
All right, so you see that getting a call from above, there's something extra you need to check, right? Because whether the sequence number is beyond the window size. If it's beyond, don't send. And getting a call from below, you receive an ACK, then you need to update the timer accordingly. Now, there are two more transitions which are a little bit more trivial.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only one packet, but this time in Go Backend, we retransmit for the entire flight of packets starting from the base to the packet right before next seek none. And the fourth transition is this: when the sender receives a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In Go Backend sender, yeah, it's actually handled here. When the sender receives an ACK, it's now corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an unacked packet somewhere and the base remains the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the Go Backend sender, or shall I say the first bit of the Go Backend sender that we actually talked last, is the initialization of the sender. Okay, so the base, starting up the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In Go Backend sender, textbook authors decide suddenly that they want to start from the sequence number 1.
All right. Yeah, so Polly was typing up a pop-up quiz. Do you like to restart the timer for the Go Backend sender when receiving a duplicate ACK? Yeah. So previously, some of you say that, hey, I don't feel comfortable if I receive a duplicate ACK, I do nothing. What about what about now in Go Backend sender? If you receive a duplicate ACK, not only you do nothing, you actually restart the timer, you wait a little bit longer. Yeah, so do you like that? Just tell from your intuition, all right? And now, hey, so far we've talked about is just the Go Backend sender side finite state machine. The receiver side finite state machine is coming next. It's very simple, only 2 transitions. One transition is triggered by receiving a new data packet. The other, therefore, is receiving old data packet or creating a gap. Okay.
Now, the receiver finite state machine of Go Backend. It's actually quite simple. Let's just skip the initialization and focus on the 2 transitions possible. Among the 2, this one is the more straightforward. We receive the data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for Go Backend again. So what it does is simply, checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted, or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer. And all we do is simply re-ACK to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
All right, so that's go back in, sender side, receiver side finite state machine. And we have a pop-up quiz that will require you to ponder. You know what? It's a perfect timing to take a break. It's now 11:12. We'll resume the lecture 11:22. So meanwhile, ponder the pop-up quiz. Do you like that the go back and sender to restart the timer receiving a duplicate ACK? All right, let's take a break. All right, welcome back. I love the conversation here related to pop-up quiz number 1, right? So I see that the general opinion is not to restart the timer on duplicate X. But you see, I like Stanley's reply the best, because he said, if the timer is restarted and the packet is actually lost, right? So here we assume that receiving duplicate AG means the packet is lost. If that's the case, of course, it doesn't make sense to delay the time to retransmit that lost packet. But what if it's not really lost, right? What if the packet is just somehow stuck and never gets to the did not get to the receiver in time or earlier than the next packet? Because that's how the sender gets a duplicate AG, thinking, hey, this packet gets stuck somewhere, it's lost. So in a way, I guess go back and sender design there tries to be careful, because the network can be complicated, and the performance at various areas on the internet can differ, right? In a very lossy network, chances higher that the packet is lost. But in a lightly congested part of the internet, right, it could be just that packet somehow gets stuck. Maybe some of the router runs some sort of priority queue, and somehow the later packet gets forwarded first. So it's a little bit hard to say. And in a way, the go back and sender design considers more cases, more scenarios, which Stanley, right, considered as well. So one of the conditions that he doesn't like retransmitting a duplicate AG or a restart timer at the duplicate AG is assuming that the packet is actually lost. Okay, so it's actually looking at the problem in a finer granularity. So guys, what I want to communicate here is that the purpose of these pop-up quiz is so that you know, it's important, of course, you learn the terms, you learn the mechanisms, RDT, go back in, and later selective repeat. But what's more important is that you see each of the mechanisms is designed somehow this way, that way. But why? And what makes go back end ended up this way eventually? So there are some considerations. Sometimes when you don't think further, when you don't debate within yourself, or in this case, guys, you guys are sharing your thoughts with each other. So when a collection of you guys, good engineers, to think together, you find reasons to say yes and reasons to say no. And from case to case, you see that, oh, yeah, maybe there are some reasons to say yes instead of just strictly saying no. And a lot of times engineering designs are like this. For this case, it better go this way. For that case, better go that way. Okay, good. Yeah, so James, right, eventually says restarting the timer makes sense too. It gives the sender more time to handle potential packet losses and keep things running smoothly. So maybe the AG will come back later. All right. So see. So engineering is based on science, of course, but engineering is the kind of science that you might have different scenarios. And for this particular scenario, you use this science. For that particular scenario, you use that science. Good? All right, very good. And we're not yet done with go back in. I'm going to show you an example of go back in. The scenario is very simple. We have a window of 4, the n equals 4. So we send 4 packets in flight. And in this scenario, we drop the 3rd packet. So the 3rd packet is lost. Okay. So this example, it's going to be long. It will take some 12 minutes to go over it. In the first part, about 6 minutes, you will see how sender send the packets back to back and updates the variables to keep the windows intact. And you will also see the receiver side receiving the first set of packets coming in, updates also some variables, and react to receiving these data packets. So 6 minutes for just this first part.
Next is to walk through an example of go back in, following the finite state machines. So then we go back and recap. Go back and sender's finite state machine and the receiver finite state machine, just so that you can follow. And real quick, the sender side of go back in is this. If we get a call from above, we check real quick whether next sequence number is within the sending window, which is base plus n. If it is, okay, then we generate packet and send it out. And then check whether we should be starting a timer. And the condition to start the timer is if this next seq number is indeed, okay, the base, and then increment the sequence number. All right, so check whether the next seq number is within the sending window. If so, generate the packet, send it out. Check whether we should start the timer. So next seq number, whether it equals the base, and then increment the next sequence number. If we do not pass the condition where the next seq number is within the sending window, then ask the application layer process to wait. All right. Now, back to the example. Let's assume the window size is 4, okay, and the sender's application layer process is sending data all the time. So sender here gets call from above all the time. So let's see. In the first call from above, all right, the base and the next seq number are both initialized to 0. Okay. Now the first call from above is going to trigger, checking whether the next seq number is within the sending window. Sending window starting from base and window size is 4. Next seq is initialized to 0. Is 0 less than 0 plus 4? Yes. So we generate the packet, send it out. And next to what? Check whether we need to start the timer. And the condition to start the timer is only when the next seq number equals the base. Next seq number is 0, base is 0. Cool. Okay. Packet 0 is indeed the first of the first flight. So start the timer here. All right. And next is just to increment the next seq number to what? 1. So next sequence number here at the beginning is 0. Now increment it to 1. So if we get a call from above again, next seq number, is it less than base, still 0, plus 4? Yes. So generate packet 1. 1 here is the next seq number, isn't it? Send it out. Check whether we should start the timer. Next seq num is 1. Base is 0, not matching. So the second packet in flight does not start timer. All right, just increment the next seq num. So here, the third call from above will start from next seq num equal to base 0 and 4. Is 2 less than 0 plus 4? Yes. So we generate yet another packet. Next seq num equal to, send it out. Do we start a timer? Next seq num equal to base 0, therefore not matching, not starting timer. Increment the sequence number to 3. Right? Is 3 less than 0 plus 4? Yes. Generate packet 3, send it out, not start the timer because next seq number is 3 and base is still 0. Right? And we increment the sequence number to 4. And now we get the fifth call from above. And that call from above will check, is 4 less than base 0 plus 4? It's no longer less, right? So what do? We go to the refuse data part of the if condition. So the application layer process is asked to wait, and sender will pause sending for now. And these packets will go out to the internet and hopefully reaching the receiver, while there's a timer that's ticking and ticking, ticking, and that is associated with the base, the packet 0. All right. And here's to quickly review the receiver of go back in. If we get a call from below, the data is not corrupted and carrying the expected sequence number, simply extract data, pass to the application layer, generate the ACK, send the ACK, and increment the expected sequence number. Otherwise, just resend the ACK that has been generated previously. Now, the receiver. Okay, receiver here will be receiving packet 0. Yeah, it's not corrupted and it's expected, right? So expecting sequence number 0, receiving sequence number 0. Therefore, we send ACK expected number 0. Next, yeah, we get a call again from below. Packet 1, not corrupted, and it's in sequence. Therefore, we send ACK for the highest data number that has correctly arrived and arriving in order. So these are being sent back to the sender. But packet 2, oops, is lost somewhere on the internet. But packet 3 will arrive. It's not corrupted, but is it expected? We're actually expecting what? Sequence number 2. So we do not extract data. We actually trigger the default transition, if you recall, and just resend the ACK that is previously generated. So ACK 1 is being sent again. So right here. All right.
All right, now the second half of the example, you will see that the sender now will react to the ACKs received and react to the timer that expired.
And now we come back to the sender side. Okay, we'll be receiving ACK 0 here. All right. So receiving ACK 0, it triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. What do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer, and it's not corrupted. What do we do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK 0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added, right? But otherwise, then we restart the timer. So hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so we cannot be stopping the timer. Instead, we should what? Restart the timer. So this timer here, original ticking, will be canceled, and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. Right? So next seek num is 4. And 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right, next seek num, 4, not equaling 1, so not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right, and then we increment the sequence number by 1, so 5 here. Okay. Similarly, receiving ACK 1, we set the base to 1 plus 1, so the base is now what? 2. Is the base identical with the next seek num, which is 5? No, therefore we do not stop timer, but instead we restart timer, so T removed there, and T is restarted with the new base, that is 2 over here. Okay, so T for 2. So this is T for 1, and this is T for 0. And at this point, one slot open up, getting call from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it out. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ACK 1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ACK 1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same. All right. Base and next seek number, still not matching. Therefore, we restart timer. Ooh, so hey, we actually killed the old timer for base 2. Now, restart timer for base 2. That means, well, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. If we get a call from above now, all right, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right? So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates react of packet 1 because they are out of order. And let's just assume these two acts is just going to take a long time to come back before T4 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate ACK2. And packet 3 arriving here, extract data, and then generate ACK3, and so on and so forth.
All right, so go back in. Whenever you receive a new ACK, you restart timer. Whenever you receive a duplicate ACK, you restart the timer. Yeah, it does look like that we are delaying the retransmission of a potentially lost packet. Okay, all the time in go back in. Guess what TCP does? Maybe TCP no longer does this. Wait until we talk about TCP sender side and see how TCP handles the timer. Now, let's move on to the second mechanism, selective repeat. This one, hey, it's actually a lot more easier to understand for human beings because one ACK for one packet, one timer for one packet. It's actually simpler. So first is introduction of the mechanism, and you will see that Polly actually introduces the mechanism. Well, actually, no, let's just give the overview first, and I'll talk about the finite state machine for selective repeat being different in the next video.
Selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go back in. So in go back in, you have cumulative ACK. So the sequence number in the ACK there is to indicate all the packets before this particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back in, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right, so receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. And the reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrive at the receiver, 2 get lost, 3 arrive at the receiver. You cannot be just extracting the data bits out of packet 1, pass it out to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order in the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. All right. So even though they're turned green, but that doesn't mean that they will include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be unact, not the maximum number of packets can be unact. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that.
All right, so that was selective repeat, and you see that in that window, you could have green packets mixing with yellow packets in the window. All right, now the second video here finally talks about the finite state machine of the selective repeat sender receiver. Here, I'm going to use a different way of writing the finite state machine. Okay, if you recall finite state machine, right? There's a state, and there are these transitions pointing out of the state. And if you recall, go back and sender and receiver. There's only just one state each, and 4 transitions for the sender, 2 transitions for the receiver. So in a way, if you think about it, it's just that you are always in this state, and it's a whole bunch of if conditions. And if you figure out which condition does what, then you can actually write a pseudo code, like a whole bunch of case 1, case 2, case 3, and case 4. So selective repeats mechanism, I'm going to write the finite state machine in a pseudo code fashion with a bunch of cases. Okay, so let's check out the finite state machine of selective repeat in pseudo code fashion.
And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. Yeah. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet, so if n here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. All right. So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1, so that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So let's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again and again, and the sender there is going to retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
Now, have you guys picked up something that's not that good in selective repeat? Those who are keen might hear this. The receiver of selective repeat now also buffer packets that's out of order and wait until the gaps are filled, then deliver a whole bunch of packets to the application. So you see that in selective repeat, it's easier to understand, it's potentially easier to implement, usually easier to understand mechanism, easier to implement. But you see that at the receiver side, the memory requirement will be higher. The receiver end of selective repeat is more complicated than the go back ends receiver. All right. So now that's similar to go back end RDT 3.0. Let's go through an example for selective repeat, which is identical to the example that we just went through for go back end. Window of 4 and the third packet gets dropped.
And that's also a walk through an example of selective repeat, just like we did one for go back end. So that example in go back end is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go back end. So window size 4, and we start from base 0 and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next C equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. All right. Now, over at the receiver side, the scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual packet, individual ACK packet, ACK 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, ACK 0 now comes back to the sender. Sender receiving ACK 0 will do what? Clear packet 0. So that packet will turn green. Is it in sequence? Yes. So we advance window. Yeah. Advance window by 1 to the next unacked packet. Upon receiving packet 1, also, yeah, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ACK for 3. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right. So this green packet, packet 3, is not the smallest unacked packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more. So still wait here. Okay, so this part of go back end and selective repeat similar. Right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ACK 4. Packet 5, buffer again, send ACK 5. And those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, yeah, timer for 2 finally expires and therefore we resend packet 2. Packet 2 goes out, received, finally, this is the smallest unacked packet, and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer. And we send back ACK for 2. All right. So, simpler.
All right, so selective repeat, easier to understand, you see, more intuitive. Now the last video is just to talk about this. Given a window size n, how many bits for the sequence number is necessary? In selective repeats case, you want to have the sequence number 2 times the window size n. And here's an extreme case to explain why that's necessary.
The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay? But from the reviewer's point of view, they will actually look the same, right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ACK 0, ACK 1, and ACK 2. So ACK 0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next ACK, that's going to advance the send base further to 2. All right. And we generate yet another packet to send. And the next one will be what? Yeah, carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? All right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK 0, ACK 1, and ACK 2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK 0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right. So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. Now, this is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the what? The application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the 2 scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent packet 0 here and packet 0 here obviously are 2 different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0 these bits again to the application layer. Not good. Right? So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay? Can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So the receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any X back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. All right? So they're actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Isn't it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window. All right? So you would never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size.
Yeah, so you see the sender side window in blue color, receiver side window in green color. So the numbers in the blue and the green should not overlap at all. And that means, yeah, the sequence number needs to be larger than or equal to 2 window size. Okay, good. And you know what? That takes us to quiz 22. And let me see. Yeah, quiz 22. And let's go to the PowerPoint mode, the slide mode here. Yeah, quiz 22. So I'm asking you to choose, okay, which pipeline RDT would you use, and more importantly, tell why. Okay, if the network bandwidth is very, very limited, would you prefer go back N or selective repeat? Okay, if the sender side memory is extremely limited, would you prefer go back N or selective repeat? Or definitely for each one of these Q1, Q2, Q3, Q4, tell why. Now, in case the receiver side memory is very limited, yeah, which mechanism uses less memory at the receiver side? And number 4, Q4, this one is more subjective. Okay, if you are to program, to choose a pipeline RDT to program yourself, to implement yourself, okay, and to you it's gonna be, hopefully to you it's gonna be a minimum effort. Okay, which one you think is minimum effort, and tell why that's minimum effort for you. All right, so let's see. Yeah, for this quiz, you guys have only 4 minutes. Okay, we have only 5 minutes to go. Okay, 4 minutes, and let's see how you guys do. All right, start counting time. All right, so I see that it seems that the popular opinion for Q1 is selective repeat because it's a more efficient use of bandwidth. I guess it's because go back N, when the timer expires, it always retransmits a whole flight of packets, right? But some of the packets might arrive at the receiver fine, but the receiver does not buffer that, unfortunately. So that's the characteristic of go back N. So on the other hand, selective repeat buffers that, then saves bandwidth. Buffers packets arriving okay at the receiver. So I think, yeah, for Q1, I think chances high that you guys will all say selective repeat. For Q2, I begin to see some sort of different opinions. So go back in from Team 20 requires less memory to store unacknowledged packets. Store unacknowledged packets from the base. So some of you says go back in. Okay, Paul, you want to be careful. In go back in, it does resend packets sometimes, even though it's correctly received at the receiver. It's just that the receiver does not buffer that. So the go back in sender actually needs to retransmit those as well. Okay. But you know what? Selective repeat buffers also packets from send base to next seek none. Even if some of them are acknowledged already. All right. So for Q2, I see majority says go back in, but it's not exactly clear why. Selective repeat, Team 9 says selective repeat. For go back in, needs store n packet. I think Team 9, you are probably seeing that it seems that at the sender side, memory is required for the packets in the window. Just for the packets in the window from the first send base. So I guess when it comes to sender side memory space to store the packets, selective repeat and go back in are the same. Don't you think so? Because within the window, even though some packets are green, you can free those, but you cannot use the memory anyway. So it seems that to track packets in flight, selective repeat, go back in, use the same amount of memory space. But guys, for Q2, maybe you can think also this. Timer is a variable. It will also take some space, memory space. Selective repeat keeps how many timers? Go back in keeps how many timers? Think about that, all right? So in a way, selective repeat and go back in, to track the packets in flight, it's always n number of packets, as long as the window size is the same. That memory requirement the same between selective repeat and go back in. And I think at the sender side, there's something being different. The number of timers. Okay, the number of timers. Go back in. Yeah, so I guess go back in is needs to store. Yeah, because selective repeat stores packet at the receiver end, obviously, if they are right out of order. So generally speaking, go back in is more efficient. Okay, receiver memory requirement. And in terms of implementation, I guess you guys have different opinions. Yeah, having just one timer and one timer retrans everything, you don't have to track which one arrives, which one did not, which one's egg arrived, which one does not. It seems easier, so I guess some of you chooses go back in. Oh, Team 1. Ricky, tell us the reason. Yeah. go back in. Oh, okay. Sherman here, representing Team 13, prefers selective repeat. Yeah, so it seems it's more clear to you, handling individual packets. So you track individual packets in a way. Yeah, it seems just one timer, and one timer to track only. Yeah, so for Q4, I begin to see more divergence. Some say go back in, but very few say selective, but some say selective repeat. Okay, good. So guys, think about this, particularly Q2. Which one requires more memory at the center end? In terms of packets to store temporarily before they can be removed, selective repeat, go back in the same. All right. Think about it a little bit more about why you choose go back in or why you choose selective repeat for Q2. Okay. Q4, it's more subjective. Good. And I see Q1 and Q3 quite obvious. Quite obvious. Very good. And that's all the time we have for this week. And about 1 p.m. you guys should receive an email letting you know the score for the exam. And there's going to be a post in the Exam 1 channel telling the distribution of the Exam 1 score, so you can see how well you do relative to the whole class. All right? With that said, I say goodbye. I see you next week. And good luck with all the midterm exams. Okay, bye.